Okay, I wanted to do one of these examples from 6.5 because I saw some repeated errors that I want to address. Here is the problem right here. They gave you this system of equations with this matrix A, 3 minus 1 minus 1, 3, and this constant vector B. You call it a constant vector because it doesn't depend on x, but it does depend on t. 4e to the 2t, 4e to the 4t. Okay, the first thing you do is find the eigenvalues, which you can do. I think you all know how to do that. To check that these are in fact the eigenvalues, you should make sure that A minus lambda I has linearly dependent rows. This is especially useful in 2 by 2. For instance, if I put lambda equals 4 into this matrix, remember that means I subtract 4 from each diagonal entry, and I would end up with 3 minus 4 in the upper corner, which would be minus 1. Minus 1 remains there. Minus 1 remains in the lower left, and you'd get 3 minus 4 in the lower right corner. So I'd end up with a matrix like this. Here you can see the rows are linearly dependent. In fact, they're the same. So this means that 4 is an eigenvalue. Now, this is a good way to check. You could check the same way with 2. You'd find that both rows turn out to be 1 the top row is 1 minus 1. The bottom row is minus 1, 1. The second row is minus 1 times the first row. Okay. Now, once you have the eigenvalues, you know how to find the eigenvectors. You simply solve the homogeneous equation. Remember, when you have a 2 by 2 case, you only need to solve the first equation and plug in 1, say, for the first entry to get the simplest eigenvector. Okay. Once you have these eigenvectors and eigenvalues, you have the reduced homogeneous solution. Now here's where I want to point out something, that the homogeneous solutions are the eigenvectors multiplied by e to the eigenvalue times t. Some people are forgetting that you need to multiply the eigenvector times e to the eigenvalue times t. So the first homogeneous solution is this column here. The second homogeneous solution is this column here. I got this column here from eigenvalue 4, eigenvector 1 minus 1. That's why I have e to the 4t from the eigenvalue 4, and 1 minus 1 from the eigenvector. I got this solution here from the second eigenvalue eigenvector pair. The e to the 2t comes from the 2, which is the eigenvalue, and I have e to the 2t times 1, 1, which is the eigenvector. So this is solution 1, and this is solution 2. So make sure when you make your fundamental matrix, make sure you include your exponential and your eigenvectors. Okay. So I want to find the inverse of this fundamental matrix V. All right, and the inverse of the fundamental matrix I can find this way. Now, a number of people are using row reduction to find the inverse of matrices. I still think for a 2 by 2, it's somewhat easier to use this formula here that you can write on your cheat sheet or whatever you want to do. If you have a matrix A, B, C, D, then the inverse is just going to be 1 over AD minus BC. You switch the two diagonal entries and you negate the off-diagonal entries. So in this case, AD minus BC is e to the 6t minus negative e to the 6t, which is 2 times e to the 6t. So that's where this comes from here. That's the same as this term here. And then to get the remaining entries of the matrix, I switch the two diagonal entries. That's why I have e to the 2t, e to the 4t here. And then I negate the off-diagonal entries, which is why these negative signs switch. Okay. And you can check, if you like, just multiply these two matrices together. Remember the row-column rule. Let's just do a couple of these. This first row multiplied by this first column gives me e to the 4t, e to the 2t, that's e to the 6t. And then I get e to the 2t times e to the 4t, which is e to the 6t. Altogether, that gives me 2e to the 6t, which cancels this 2e to the 6t. That would give me a 1 in the upper left when I multiply these two matrices. That's what I want because I want them to multiply to be the identity matrix. Let's do the second one. If I do this first row times the second column, I'm going to have e to the 4t times e to the minus 2t, minus e to the 2t. That's minus e to the 6t. And then here you'd have e to the 2t times e to the 4t. That's e to the 6t. That gives you 0. So you can actually check that every one of the 4 entries of the product v of t times v of t inverse is equal to 0. Once you have v of t inverse, you can multiply by the vector b. The vector b doesn't appear on the screen anymore. But I can just remind you that b was equal to 4e to the 2t times 4e to the 4t. When you multiply these out, I can leave this out front if I want while I'm multiplying, and I left it out here. So when I do the multiplication, I end up with this vector here. And then you integrate. These are easy to integrate. You integrate term by term. Integrate e to the minus 2t, ends up dividing by minus 2. Integrate minus 2 gives you minus 2t. That's this term here. The final result of the integration, if you, like I said, you integrate this, you get this. If you integrate the minus 2, you get the minus 2t. If you integrate this 2, you get a 2t. If you integrate 2e to the 2t, you get e to the 2t. Now notice I'm not worrying about integral limits. And that can cause a problem if you don't do things the right way. I'm not using the equation in the book that uses definite integral limits. I'm just doing an indefinite integral. So this is an indefinite integral. I think this way is easier. It involves less algebra. So once I found this indefinite integral, then I've got one more stage to my solution. If you remember, the formula looks like this. You have x is equal to v of t plus v of t times the integral of v of t inverse times b. Now I forgot this. In here there's going to be a times constant. V of t times constant. Alright, so we've taken care of this part. We found v of t inverse times b. We've integrated it. We need to multiply by v of t. That's just a simple matrix vector multiplication. I end up with this here. Minus e to the 2t minus 2t e to the 4t plus 2t e to the 2t plus e to the 4t. That's on the top. On the bottom, e to the 2t plus 2t e to the 4t plus 2t e to the 2t plus e to the 4t. Okay. The last stage is to find my initial condition. I didn't state my initial condition up here, but it was x of 0 is equal to 1, 1. Okay, x of 0 equal 1, 1. That's what I've rewritten right here. And I'm going to use this x of t equals v of t times a constant vector plus this term that I've already computed. Now rather than using the formula in the book with indefinite intervals, I'm just going to plug things in and solve for the initial conditions. I'm just going to take this equation and plug in t equals 0. And I highly recommend you do the same thing. So on the left hand side, x of t, we know x of 0 is 1, 1, so that's where the 1, 1 comes from. Then you have to figure out what v of t is at t equals 0. If you plug in for t equals 0, v of t has all exponentials in it. Every exponential becomes a 1 when you have t equals 0. And if you look back at what v of t is, this is the result you get for v of t when t equals 0. Alright, that's what has to multiply the C1 plus C1, C2. And then I have the leftover, which was this part here. I have to plug t equals 0 into there. That's not as difficult as it looks. If I have something here like this is 2t e to the 4t, well, that's going to become a 0 when t equals 0. 2t e to the 2t, that's going to become a 0 when t equals 0. The only terms that are not 0 are the ones with just e to the power, and this e to the 2t, for instance, is going to become 1 when I put t equals 0. So altogether, I'm going to get minus 1 from here, plus 1 from here. That's going to give me this 0 here. And then here I'm going to get a 1, and then a plus 1. That's going to give me a 2 there. All right, so this is my matrix equation for C1, C2. And you can solve that easily using methods that you know. Actually, bringing the 0, 2 to the other side gives you this even simpler matrix equation. Okay, that's it.